Hello everybody. So now we will continue our lecture on duality theorems. So I will start from the canonical format of duality. So when the primal of the problem is the max problem and x is the decision variable, so the canonical format of the primal problem will be like this. All the constraints will have larger than or equal to sign, and all the decision variables or the x must be non-negative. And the canonical format of the dual, so when the primal is a max problem, then the dual will be a min problem with w as the decision variable, and all constraints will have the sign of smaller than or equal to, and all decision variable are non-negative. This is the relationship between the primal and the dual. When the primal have an optimal solution, then the dual will have an optimal solution also, and the value of the z star, or the value of the optimal objective function of the primal, and the optimal value of the objective function of the dual will be the same. So when the primal or the dual is unbounded, then the dual or the primal will be invisible. And when the primal is invisible, then the dual will be unbounded or invisible. So here are the equations that we can use in order to find the optimal solution of the primal or the optimal solution of the dual when one of them is known or is given. So the z star of the primal will be equal to the z star of the dual. So when you have a primal problem and that problem is has an optimal solution, so the z star of the primal and the z star of the dual will be the same. So the second equation, so if we know the dual of the problem and we have the solution of the dual, then we can calculate the optimal solution of the primal by using this equation. So the optimal solution of the primal will be the C basis of the dual times B inverse of the dual. So C basis of the dual means the coefficient of the basic variables. The coefficient of the basic variable in the objective function value of the dual times the B inverse of the dual. So the optimal solution of the dual, W star, will be C basis of the primal times B inverse of the primal. So C basis of the primal means the coefficient of the basic variable in the objective function in the objective function equation of the primal. So the B inverse, if we solve the problem by using simplex method, so we can find the B inverse directly from the simplex table or from the revised simplex table. So now let's solve this problem. So we have a, a mean problem, and on this problem we have four objective function four, not four objective function, we have four decision variables, and the problem has two constraints. So what we're gonna do, so we need to get the dual of the problem, and then we solve the dual uh, by using the graphical method. So as you can see, the problem has only two constraints. So we're gonna have W1 and W2 as the decision variable of the dual. So because the dual will have only two decision variables, so we can solve the dual by using the graphical method. Now, based on the solution of the dual, we will find the, the solution of the primal. So this is the problem. So I already copy the problem to this window. So remember, it is a mean problem, and this is the weak duality theorem for the mean problem, where the z star must be bigger than or equal to the linear combination of the right hand side, and that must be bigger than or equal to the linear combination of the right hand side. So the thing that we will do, we'll do A first. We will get the dual of the problem. So we need so we will have two dual variable W1, and we need to decide the sign of W1. See here, from the weak duality theorem, the left hand the left hand side must be bigger than or equal to the right hand side, and see here the left hand side is bigger than or equal to the right hand side. So the first constraint is following the weak duality theorem. So in order not to change that, so W1 must be non-negative. Now constraint number 2, you see the sign, it is less than or equal to, but it must be bigger than or equal to, so that it will follow the weak duality theorem. So in order to change the sign, so we need W2, and that W2 must be negative or 0. Okay, so now let's do the multiplication. So we'll have W1 W1 minus 2W2 and times x1, and according to the weak duality theorem, the linear combination of the left hand side must be less than or equal to the z star. So this must be less than or equal to then 2x1, and see, x1 is positive, so it will not change the sign. So this is it, and then for the x2, it will be 6w1 plus 5w2 times x2, and that must be less than or equal to 15x2, and x2 is positive, so we are okay. And then 3w1 minus w2 times x3, and that is must be less than or equal to 5x3. So x3 is positive, so we are okay. And then w1 plus 3w2 times x4, and that must be less than or equal to 6x4. x4 is positive, so we are okay. And now we need to do the multiplication for the right hand side, so we'll have 2w1 minus 3w2. Okay, and from this one we have w1 positive and w2 negative or 0. Okay, so here we can cancel x1, can cancel x2, can cancel x3, and we can cancel x4. And for this one, so we get this from the right hand side, so we need to make the right hand side as close as possible to the z star. So because it is less than the z star, so we need to max the 2w1 minus 3w2. So now what we have here is just the another LP, and that LP is the dual of this problem. So the dual is max 2w1 minus 3w2, and then w1 minus 2w2 less than or equal to 6w1 plus 5w2 less than or equal 15, 3w1 minus w2 less than or equal to 5, w1 plus 3w2 less than or equal 6, and then w1 non-negative and w2 non-positive. So this is the dual. So this is the answer for problem A. Now we will solve problem B. So we need to solve this problem by using the graphical method. It is possible because we just have 2w, which are w1 and w2. So I'm gonna copy this problem. Okay. So this is the dual, and we will solve the dual by using the graphical method. So this is the axis, so we will have 1 over here and 2, 3, 4, 5 and 6, and this is 1, 2, 2, and then 3, 4, and 5. So here we'll have -1, -2, -3, -4, and -5. this is the axis for W2 and this is the axis for W1. So constraint number 1, so the intersection will be -1 and 2, so -1 over here and 2 with W1. Okay. Constraint number 2, so with W2 it will be 3 and with W1 will be 15 over 6. Those are the intersection. 15 over 6 means 5 over 3, so that is less than 1. So we will have 3, that is less than 2, 15 over 6. So it's, but okay, so it's something like this. Okay. Okay. This is constraint number 2, so I will mark it. So this is constraint 1. This is constraint 2. And then constraint number 3. So for W1 it will, for W2 it will be -5. -5, and for W1 it will be 5 over 3, so something like this. Okay. So I think I made a mistake with constraint number 2, so it's constraint number 3. For constraint number 2, this will be W2, it will be 3, and with W1 it will be 15 over 6. 15 over 6, that will be 5 over 2, which will 2.5. Okay, so I need to, so this is 2.5. Okay, so this is for constraint number 2. Now constraint number 4 with 6 and 2, 6 with W1 and 2 with W2. So 6 and 2. Okay. Okay, and we have W1 positive, so W1 positive, so this is it. Sorry. And then we have W2 negative, so this is the direction of W2 negative. Okay, and see that every constraint have the sign of less than or equal to. So if we test 0, 0, so 0 is less than or equal to 2, 0 is less than or equal to 15, and so on and so forth. So every constraint will have the same direction. So every constraint will have the same direction. So the direction is to the 0, 0, or to the origin. Okay. Okay, so now we need to identify our feasible region. So I think this is the feasible region. oops, sorry. I think oh, I need to do this better. So okay, this is the visible region. Okay, okay, so the visible region is given by constraint number 1 and constraint number 3. Okay, remember that the visible region is given by constraint number 1 and constraint number 3. So the intersection point over here, so if we do the math, it will be a over 5 comma minus 1 over 5. So that is this point. Okay, need to move that a little bit, and then this is minus 1 over here, and this is 5 over 3. So this point is 5 over 3 comma 0, and this point over here is 0 comma minus 1. Okay, so this is that point, and this is this point. So okay, so now we need to test those 4 points. Actually we have 4 points because here it is 0 comma 0. So z is 0 for 0 comma 0, and then z is let's see, minus 1 w2 3 for 0 comma minus 1, and z equal, let's see, 2 times 5 over 3, that is 10 over 3 for 5 over 3 comma 0, and z equal 19 over 5 for a over 5 comma minus 1 over 5. So it is clear that a over 5 comma minus 1 over 5 is the solution of the dual. So w1 star is a over 5, and w2 is minus 1 over 5. So I'm gonna copy everything to this window. Okay, and remember that the visible region over here, it is given by constraint number 1 and constraint number 3. So this is constraint number 1, okay, and constraint 1 2 3. Okay, so the matrix B that will be, so constraint number, so the matrix B is defined by the visible region. So the visible region is given by constraint number 1 and constraint number 3. So your matrix B is 1 minus 2, and then 3 and minus 1. That's your B matrix. Okay, so this is a matrix. Okay, and the B inverse, So the B inverse, so that will be the inverse of this matrix, and I assume that everybody knows how to find the inverse of a 2 by 2 matrix. And if we do the calculation, the B inverse will be minus 1 over 5, and then 2 over 5, so I'm gonna do this, and then minus 3 over 5, and 1 over 5. So this is your B inverse matrix. Okay, so this is an inverse, so this means inverse. This is B inverse. Okay, now the problem number 3, so we need to find the solution of the primal by using the information that we have from the dual. So we can use this equation. Okay, this equation. So x prime primal will be C basis dual times B inverse dual. So we have the B inverse dual. And what is the basis of the dual? The basis variable of the dual, it will be W1 and W2. See here, this is for W1 and this is for W2. And that is the value of W1 star, and that's equal A over 5. And the value of W star, and that is equal minus 1 over 5. Okay, so for the primal, the basis will be x1. So we will have x1 star, because the basis or the B matrix of the dual is given by the first constraint. So the first constraint of the dual corresponds to the first decision variable of the primal. So we'll have x3 star over here. Okay, and therefore, so x1 star comma x3 star equal C basis of the dual. What is the C basis of the dual? 2 and minus 3, 2 and minus 3, 2 minus 3 times the B inverse of the dual. So minus 1 over 5, 2 over 5, minus 3 over 5, and then 1 over 5. And when you do the calculation, you will have 7 over 5 and 1 over 5. So that's the solution for the primal. So this is the primal. See the problem again. So x1 equal 7 over 5, and x3 star equal 1 over 5. x2 and x4, they are non-basis, so their value are 0. So x2 star equal x4 star, and they are 0. And what is the z star of the primal? It should be 19 over 5. So because when the dual is optimal, then the primal is optimal, and the value of the z star must be the same. So you can test it. 7 over 5, 1 over 5. So 2 times 7 over 5, and that is 14 over 5 plus 5 times 1 over 5, and that is 5 over 5, and we can, and the result is 19 over 5. I think that is it with the duality theorem. Thank you very much.